Hello, I'm going to give a brief tutorial on the nucleophilic substitution reaction of a tertiary alcohol. Please note that this is acid catalyzed reaction. Before we begin, I wanted to discuss and to remind you that two important questions that should be addressed are what can be the nucleophile and then what can be attacked. We always attack from things that are either negative or delta minus or more electronegative, and that it always attacks something that's positive, delta plus, or less electronegative. Okay, a nucleophile has to have lone pair electrons to do the attacking. The example that I wanted to do right now is the conversion of 1-methylcyclohexanol, an alcohol, into an alkyl halide. And we're going to use our good friend hydrobromic acid as the acid for catalysis here. So first, let's draw the compound in question. So we have to have a cyclohexane. And it should be noted that in a future chapter, we're going to learn that this mechanism is true for tertiary alcohols, but primary alcohols undergo a different reaction mechanism. Remember, HBr in the presence of alcohols and water really look like H3O plus and Br minus. So I'm going to draw it as such. And I'll try to use a different color for the acid. Okay, here we go. Now, the first thing that should be noted is the fact that we need to know what is delta minus or negatively charged that can serve as a nucleophile. And this is a substitution reaction, so ultimately we will be substituting one functional group for another functional group. Here, the objects that have, or the elements that have lone pair electrons are the two oxygens, the one in the alcohol, the one in the acid, and then we also have the Br minus. What will happen first is that the alcohol will become protonated. That's the first step of this mechanism. So, boom, it goes and swipes a hydrogen, because that's what acids do. Remember, they donate hydrogens. And these two electrons stay with the parent oxygen. This is reversible and it's fast. We're going to see that often that's true, that for us, protonation steps typically are going to be reversible and fast. So now the oxygen is protonated. And we have a water that's left behind from the original acid. And we still have the Br minus. So, now we have what becomes the rate limiting step, and that's the dissociation of what will be a water to form a carbocation. Okay, so what happens here is this oxygen will leave and take both of its electrons with it. Okay, so it's going to form the carbocation. This is the slow step. or the rate limiting step of the reaction. So now we have a methyl cyclohexyl carbocation. We have a water that has left. We have technically the water from before, which in reality we can't tell one water from the other. And then last but not least, we have the bromine. So for the final step, which is a fast step, it is the nucleophilic attack. So what do we have around here that can be a nucleophile? Well, it must have lone pair electrons, so you could say it's one of the waters, which is true, but if a water comes back and attacks the cation, you're just going to reform your alkyl oxonium ion. So instead, the only other option we have is this bromine, because remember, it has 8 lone electrons around it. And so, the bromine now comes in and attacks the carbocation. And in doing so, and this is a very fast reaction, we're going to form the following organic product. And last but not least, we need to name our product according to IUPAC standards. Once again, it must be in alphabetical order according oops. One bromo, one methyl cyclohexane. Whoops. One bromo, one methyl cyclohexane. So now, on the next slide, I'm going to give you a sample problem, and then I want you to pause the video and see what product you form. So, for your problem, I want you to do the substitution reaction of 2,4-dimethyl-2-pentanol using hydrochloric acid. That's using HCl. And so at this time, you should pause the movie and try to work through the mechanism yourself to find out what the final product would be. Make sure that you can name that according to IUPAC standards. So now, I'll work through this mechanism with you. First off, I'm going to give you a hint. Only look at this ground zero carbon. So everything else is just window dressing. So we're going to call it R. So that will make writing out the mechanism much more simple. So let's just rewrite what we have. So that means that we're going to have the ground zero carbon with 2 methyl groups hanging off R, and the alcohol. we have the hydrochloric acid, which will look like H3O plus, and the chlorine would be minus. The first step is protonation. Remember, it's fast and reversible. And so we'll be left with the alkyl oxonium ion, a water molecule, and the Cl minus. The second step which I'll put in a different color. The second step is the formation of the carbocation, and it is the rate limiting step. It's where this water molecule, or what become water molecule, will leave the carbon that it's attached, and it takes the 2 electrons along with it. So it takes these 2 electrons and it's the slow step, or the rate limiting step. And we get the water that had been attached, and the formation of the carbocation. Finally, the third step, which is the fast step, is where the nucleophile, which in this instance is chlorine, will come in and it will attack that carbocation. Once again, this is a fast step, and we're going to be left with the following compound. Now, all I'm going to do is redraw. Whoops, sorry about that. I'm going to redraw the R group. So I'm going to scroll everything up. And this is what the final product will be. We have the chlorine attached to what I call the ground zero carbon, methyl, methyl, and then the R group. Finally, we just need to name it. According to IUPAC standards. Chlorine comes first in alphabetical order. So it's 2-chloro, 2,4, dimethyl pentane. Two-chloro, 2,4-dimethylpentane. So hopefully this has helped you with the idea of a nucleophilic substitution reaction.